Hello students, today we are going to study two very important effects. These effects are you have in your syllabus, that is the syllabus of sensors and transducer. They are Villari effect and this Hall effect. As I have underlined here, this effect was named as per the inventor of this effect, that is Italian physicist Dr. E. Villari. Okay. Before starting our discussion regarding Villari effect, we should know a very important term, that is magnetostriction. What is magnetostriction? The effect of mechanical deformation. We have three types of mechanical deformation mainly, and they are stretching, twisting and bending. So the effect of mechanical deformation on the magnetization of a ferromagnetic material, for example iron, is known as magnetostriction. The Villari effect, as it is given, this effect is the opposite of magnetostriction. Okay, that is change of size of ferromagnetic material during magnetization. That means, as per magnetostriction, we know that due to the external mechanical force, the magnetic property of the ferromagnetic material can get changed. But as per the Villari effect, due to the magnetization force, the shape or the size of the ferromagnetic material can get changed. That means it is directly opposite to the Villari effect, this magnetostriction. Clear? We know nickel is a ferromagnetic material, right? And that shrink during magnetization. That means if you apply any external magnetic force to nickel, then it will get shrink, and so this can be referred as negative magnetostriction. So I think it is clear to you what is Villari effect. And also in this incident, this ferromagnetic material lose some of their magnetic qualities when stressed. That means again it is same as negative Villari effect. Clear? On the other hand, the stretching of ferromagnetic material with positive magnetostriction. What is positive magnetostriction? It is explained here. For example, a bar of iron nickel alloy with 65% of nickel, this kind of alloy leads to an increase in their magnetic properties. That means increment in magnetic properties here referred as positive Villari effect. So due to stretching, the magnetic property can get enhanced for such kind of alloy. Now, during compression, the sign of the Villari effect switches to its opposite, right? It is for the compression, and the Villari effect is explained by the fact that the domain structure of ferromagnetic, which determines its properties, changes when mechanical force is applied. So this is the basic thing about the Villari effect. It is used in creating materials with given magnetic properties. That is the application. So in short, this is the basic about the Villari effect. Next, we are going to start another very important phenomena in view of the domain of the physics, and which is important for your syllabus also, and which is Hall effect. Now, whenever, as it is written here, we place a current carrying conductor in a magnetic field, what happens? There is a deflection of charge carriers due to influence of magnetic field in the conductor body. There will be an external force which will act on the current carrying conductor. This is the basic thing. And this phenomena, this typical phenomena, is referred as the Hall effect, as per the name of its inventor, Edwin Hall. Clear? This is the Hall effect. Mainly, Lorentz force is responsible for Hall effect. That means the force on the current carrying conductor, and when the current carrying conductor is placed inside a magnetic field. It is known to us that when we place a current carrying conductor inside a magnetic field, the conductor experiences a mechanical force to a direction depending upon the direction of the magnetic field. and the direction of the current in the conductor. That means we can easily find out or determine this direction of force. So the electric current means a flow of charge. Basically, current means flow of charge to a specific direction. In metal, it is entirely due to the flow of electrons. Obviously, electron flows are normally referred as the flow of current. In semiconductor, it is due to the flow of free electrons. There are a vast amount of free electrons within the semiconductor, as well as holes also. Here holes refers the positive charge. In semiconductor, holes move in the direction of conventional current and free electrons move in the opposite direction of the conventional current. It is very common and known to all of us. As the electrons have charge, they experience a force while flowing through a conductor placed inside a magnetic field. So the electrons will experience a force inside a magnetic field. Due to this force, the electron get diverted towards one side of the conducted during flowing, right? As the flowing of the charges get shifted to one side of the conductor, there may be a tiny potential difference appear across the cross section of the conductor. So there is a measurable potential difference across the cross section, that means across the between the two sides of the conductor. We call this entire phenomena. That means due to the external magnetic effect, there will be a measurable or considerable potential difference between the two sides of a tiny metallic strip, and this effect is known as Hall effect.